Okay, so we'll start this lab. So this is lab 2 in the review sessions, and in this lab we're going to talk about the language modeling and especially the n-gram models, and we're going to build n-gram models. Okay, so we'll start with the imports, and the first function here is the data loader. So it takes the file name, the data file, and it processes it. So the data file is an example of a big text, an English text, and it returns two objects. So the first object is a list of lists. So it's a list that contains list, and each list is a sentence from the text. Okay. So each sentence starts with the start token and ends with the end token, and then after that the function builds a dictionary. So this dictionary maps each word to the number of times it appears in the text. Okay, you don't need to worry about the implementation, you just need to know what the function does for you. Okay, so here we're going to load the training text using the load data, and you're going to see an example of the train data. So we're going to print the first sentence using train data of 0, and we're going to access the dictionary vocab to see the number of words, the number of times the word how appears. So let's run this cell, and so this is the first sentence in the text. So I liked your idea and I adopted it. As you can see, the first token is the start token and the last token is the end token. So this is the same for the entire text. And in order to find the number of words, the number of times the word appear, you just need to access dictionary using the key, which is the word itself. And here we printed how, so how appeared 3,195 times. And then we also loaded the validation data, which we are going to use to check if our n-grams works, generalizes fine. Okay, so far so good. Okay, so the first function which you are going to try to implement is remove rare words, because there's some words in your data that are very rare. You are going to replace these words with the unknown token, this token. Okay, so as you read in the slides, this technique can be used in order to improve the way n-grams work, because the rare words can affect your n-grams, and because some of the n-grams will have a value of 0, and if they don't appear in your will have a value of 0 in your validation set if they don't appear in your test set. So that's why we are going to remove the rare words, and so the condition here is the min count. So we will replace the words that they have a count that's less than min count. In this case, by default, the min count is 1. You can try different values and see. So that's acts like a hyperparameter that you're going to use. So we'll give you let's say 5 minutes to try to implement it, and then I'm going to implement it for you. So the parameters for this function is data, so it's a list of lists. So it's the same train data that we loaded here. Okay, and we have a vocab, which is the dictionary, the same dictionary also. We got the one we got here, and we have min count, so this is integer, so this is the number of words, the minimum count. Okay, and then we are going to return the data, so it's a list of lists just like the original data, but with the rare words that should be replaced with the unknown token. Okay, so data and data with unknown, they are the same. They should look the same, but with different in some particular. Okay, so in order to do that, we're going to have two for loops. We are going to loop for all the sentences, and then we are going to loop for the words in the sentence, and then we are going to replace the word by the unknown token if it has a count that's less than main count. So we'll do for sentence in data, and then we'll create sentence with unknown, which this is going to contain our new sentence. Okay, and then we'll do for word in sentence. Okay, now if word in vocab, so if the word exists in our vocabulary, so this is, we'll check if the word exists in the keys of the dictionary, and vocab of word is larger than min count. Okay, sentence with unknown dot append word. Okay, else sentence with unknown dot append the unknown token. So the unknown token will be like this, and the final step is we're going to append this new sentence to data with unknown. So data with unknown dot append sentence with unknown. Okay, so we'll do a for loop for all the sentences on our data. We'll create the new sentence. Okay, and then we'll do a for loop for all the words in the sentence, and then we're going to append the word if it has a count that's larger than the min count. Else we're going to append the unknown token, and then we're going to append this sentence to the data with unknown list. All right, now let's see if our function works. Let's try to see our new training data. So let's see if there is some unknown. Yes, so this example of a sentence, we have the unknown token here, so I believe it works fine. All right, so this is the core of our tutorial, is building the n-gram model. So what's a language model? The language model is estimating the probability of a sentence. So here we need to build the n-gram models, and so n here is the size of a gram. So if n is 1, you're going to build unigram. If n is 2, you're going to build the bigram. But in our case, because we are going to use the backoff model, you are going to build the n-gram and all the smaller n-grams. So if n is 3, you need to build the 3-gram model and the bigram model and the unigram model. So what is a n-gram? So this is what you are going to write. So you need to build a dictionary of dictionaries. So it's a dictionary that maps to a dictionary. So the key to the first dictionary is the context. So it's going to be my n-gram, my smaller n-gram, and then this is also going to map to a dictionary that maps each word to the probability. So in order to do that, you are going to first build a dictionary of the counts. So it's a dictionary of dictionaries, and then you are going to build the probabilities from that counts. Okay, so because it's a little bit tricky, I'm going to write it to you, and then I will explain it to you directly. So because it's going to take time for you to implement it, I will do it first. Okay, so let's first build the counts. So we'll do for sentence in data. First, I'm going to convert the sentence into a tuple because in Python you can't have a value. You can have the key of a dictionary to be a list, but a tuple you can use a tuple because in this case we need to have a gram. We need to have 3 words to be the key of a dictionary, and the 4th word to be the value. Okay, so that's why I'm going to convert my list into a tuple, because I can use a tuple as the key of a dictionary. Okay, now we'll convert the sentence. So this is what I've done here for sentence in data, and then I converted the sentence to be a tuple. So now sentence is a tuple, and now I can send it into a dictionary. Okay, and now for I in range len of sentence. Okay, have total number words plus equal 1. We just need to calculate the total number of words. And now for k in range n, because I'm going to populate my dictionary with all with the n gram, and then the n minus 1 gram, and then n minus 2 gram, until I reach 1. Okay, because we're going to use the back of counts. Here is the dictionary that maps each context to, so it's the same as probability, but it maps the context to a dictionary, and then in this dictionary there is the word, but instead of probability of the word given in the text, we have the count of the word. So the probability dictionary is going to be the same as the count dictionary after we divide by the number of the words here. So to convert into probabilities. Okay, I will build the counts for you. Okay, so if I minus k is less than 0, break counts of sentence of I minus k to I of sentence of I plus equals 1. Okay, so what I've done here is I will start populating the counts dictionary. So for every sentence here, okay, I minus k up to I is I'm indexing the sentence from the for the words that are previous to the word I up to k. So if k is 3, I need to look back for the 3 words before the word I. Okay, and the reason I've done this break here, because suppose I'm at the start of the sentence, I can't go back in history 3 words. Okay, so if I'm at 2, I can only go back 2 elements, but I can't go to the 3rd element. That's why if I minus k is less than 0, just ignore this and continue to the next word. So it will ignore the first few words until we have size n gram. Okay, and we'll do this for n equals 0, for n equals 1, for n equals 3, n equal 2 and equals 3. So we'll do it for all n minus 1 gram, because in our dictionary we're going to build, if n is 5, we're going to build the 5 gram, the 4 gram, the 3rd gram, the 2nd gram, and the bigrams. We're going to use all of them. Okay, so now after populating our counts, we're going to estimate the probabilities. Okay, so first, for context in counts.keys, so we have the context here, which is going to be my n-gram. Okay, we need to convert the counts into probabilities in the probability dictionary. So what I'm going to do here is start for every context. I will have a variable denom, which is the denominator that I'm going to divide with, equals equals 0, and then for w in counts of context dot keys, denom plus equals counts of context, okay, of the word w. So for every word I will increase the count of the denominator, okay, and after I do that, now for every word in counts of context dot keys, the probability of that word, of the context of that word, is going to be the count, the context of that word divided by the denominator. Okay, so I will explain it again. When we were doing the n-gram models, we know that in order to find the probability of let me show you the formula. So the probability of a word given its history is the count of the number of times the word appears given the history divided by the number of times its history appears. Okay, so in order to find the number of times the word appears given its history, it's straightforward. We get it from the dictionary, but the denominator here we need to calculate it. So what I did here is I calculated the number of times every word appears after this history. Okay, so it will give me the total of time the history of the word appears. It's like let me show you an example here. Suppose my dictionary has something like this is a cat, this is a dog, this is a tree. Now suppose I need to estimate the probability of cat given its history. So from the dictionary I can get that directly because I can do counts of context of w. It will give me the number of time cat appears given its context. But in order to find the number of time this is a appears, I will calculate the number of time cat appears after this is a. I will calculate the number. I will add to it the number of time dog appears after this is a. I will calculate the number of times tree appears after this is a. So when I calculate all of them, then this is going to be my denominator. So this is what I've done here. Okay, so I calculated the number of times all the words appears after this particular context, and then when I divide by this number, when I divide the count of the word of my particular word given its context, when I divide it by the total number of time all the words appear after my particular context, is going to give me the probability of the right. Let me first check if it works fine, and it appears to be working fine. So okay, so let's check if it works. So here we define n to be equals 2. So we'll build a bigram model, okay, and but we'll have the bigram and we'll also have the n-gram model as well in our model, and let's see if it works. So maybe we can do it later because so model is a dictionary. One thing we can do is for key, let's say for context, and let's say for key value in model.items. Let's do print key and value, and let's see what does the model looks like. So it's big, so it's a dictionary and it maps here to a dictionary, and we'll have a word, and then it maps the probability of that word, and then we have another word. So all of them, they belong to the first context. Okay, so that's our dictionary, and now we can get rid of it. Okay, so so the next function that we need to implement is the function that gives us the probability of a word given in context. So one thing that will come into your mind is we can directly call because we need to find the probability of the word W given a context. We can do model of context and W. Okay, but here in this case we are going to use the stupid backoff model, which you have seen in the slides. So I'm going to move to the slides to explain it to you, and then I will show you how to implement it. Okay, so this is the stupid backoff model. So what it tells you is that in order to get the probability of an n-gram, so the probability of a word given its context, okay, if the count of the word is larger than 1, so if the word appears in your model or in your data, if the count of the words appear in your data, this is going to be the count of the word given your context divided by the number of times the context appears. But what if this word doesn't appear, if this word WT doesn't appear in your data? So because we don't want the word to have 0 probability, we can use Laplace smoothing, we can use different techniques, but one of the techniques is the backoff. So we are going to move to the smaller n plus 1 gram. So let me explain to you with an example. Suppose we have the same data we used before. This is a car, this is a dog, and this is tree. Suppose we have something like this, and we need to estimate the probability of let's say tree given. Suppose in my test data there's a sentence like this is a tree. Okay, and now okay, let me change this to that is a tree. And suppose I have something like this. This is a tree in my validation set, but this is my training set. So I will have a count of tree given this is to be 0. But I can change that with if I look at tree given is okay, I can count this probability and then use it. I don't need to look for the entire history. I can go back to the smaller gram. So instead of using 3 words in my past, so instead of using a 4 gram model, I can use a 3 gram model, so given the 2 words before this word. So, and my probability in this case, so the probability of this, of 3 given this is going to be 0.4 times 3 given is okay. So the number 0.4 here is empirical, so there is no theory behind why they chosen the 0.4. They just they've done a lot of experiments and they found this number works the best. Okay, so this is why we in the first place, when we built the probabilities dictionary, we tried to find the probabilities of so we wanted the probability of the n-gram model, but we calculated the probabilities for the n-gram model, for the n-1 gram, for the n-2 gram, and so on and so forth, in order to use it in our backoff model. Okay, So to solve it now, the formula says if the count is larger than 0, we can use the direct formula with the counts. If it's not larger than 0, so if it's equals 0, then we can use the probability of the smaller gram. We multiply by 0.4, and if it doesn't appear in the n-1 gram, we will multiply 0.4 times 0.4 times the probability of the n-2 gram. So we're going to go recursively until we find the gram that the word that guarantees that the word appears. Okay, so I hope you are familiar with Python recursions, and to do that we first check if the word is in our context. I will check if the context is in model and the word appears in the model, so and W in model of context. If that's true, then we're going to return the model of context W. Okay, so model here is it's the probabilities that I got here. So this is my language model. So the language model, which is a mapping from the context of a word given context to its probability. Okay, and if this is not the case, if it's not found, else what we do here, we're going to return 0.4 times get proba of our model and context of from 1 to the end of it. So here we used a smaller n-gram. Okay, so we didn't start from the first word, we start from the second word, and we've gone till the end of our model. So we're going to use the probability of my word given the smaller gram. So this is going to be done recursively until we find. Okay, so let's look at the next function which we are going to use. So we need to implement the function that computes the perplexity of our model. Okay, and let's see. So let's move to the slides to look at what the perplexity means. I know you already know it, but just to make sure. So the perplexity was in slides 43. So the perplexity of a sentence is the product of the probabilities of the sentence of the n-gram models, okay, all scaled to the value -1 divided by the length of the sequence. So it tells us how probable my sentence is. Okay, so because the probabilities are small values, and then when we multiply them by themselves, they get smaller and smaller. It's better to use the log probability. So this is the negative log likelihood. So if I have a sentence given a model and I need to compute the perplexity of that sentence, I compute the probability of a word given the sentence, or given the n-gram, or given its context, and I sum all the log probabilities for all the words in the sentence, and that gives me the probability of that sentence. Okay, so it's very straightforward, and we are going to use, so in our function model here is the probabilities that I calculated here. Okay, but we're going to use the get probability function instead of looking directly to the probability to the dictionary, because now we have the function that gives me the probability of a word given its context, and it uses the backup model. Okay, so the function here takes my model, so this is the same model that I used, the probabilities that we estimated them, and then the data. So this is this is the text that I need to find its probability. So it's going to be a list of lists each list is contains of a sentence, and then we have the size of the n gram. Okay. So first we have the perplexity and the length of sequence initialized. So the perplexity is 0.0 because it's a float number, and the length of the sequence initially is going to be 0. So I'm going to increase the length of the sentence as I go for all the words. So first I'm going to do a for loop for all the sentences. So for sentence in data, okay, and now sentence is going to be a tuple of the sentence. I'm going to convert it into tuples because into a tuple because I need to use it in dictionary, okay, because I can't use a list. And now for I in range, sorry, for I in range, the length from 1 to the length of my sentence. Okay, so I will define a word, a variable nc, which is the number of the context to be the minimum of n minus 1 of I, because suppose my n-gram is 2 and I am at the beginning of a sentence, so I don't need to look at the history because in the beginning, if I'm at the start talking, I can't look back. I can only start calculating after I am at the second item, okay, in my sentence. So my context is going to be the sentence from I minus nc up to I, okay, and the perplexity is going to be, so I'm going to add to the perplexity of a model the negative log, okay, of get proper of my using the model, the context, and the word. So the word here is sentence of I, okay. So first here I choose my context, so it's from I, it's from I here. So let's do it with an example. So this is 3. So this is my I, and this is the past. So it's I minus nc, okay. And this I subtract nc is the minimum of n minus 1 of I, because if I am here, I don't need to look back. If I am here, I need to look back at 1 word. If I'm here, I need to look back at 2 words. And if I'm here, I need to look back at 3 words. And if I'm here, I need to look back at 3 words. If I'm here, I need to look at these 3 words. So, but it's only going to work when my history is smaller than my n-gram, okay? So that's why I did this minimum. Okay. Now, after I calculate the perplexity using the get proper function, now I will increase the length of my the number of words in my sentence in my data, and now the perplexity is going to be the exponential of that. So mass.exp perplexity divided by t, okay. First I took the sum of the logs and then I did the exponentiation. Right, let's see if it works. Oh, okay. So it's per, not per. Yeah, it's get prop, right? Yeah. So the perplexity for my validation data is 50. Now let's see for the train data. I suppose going to be, yes, it's smaller as expected because I calculated the words for my I calculated the models, the probabilities from my training data, so the perplexity should definitely be smaller than the perplexity with my validation data. Okay, because my validation data will have some off vocabulary words. I think we need to build the model first. Let's say suppose n equals 4. This will take a bit of time. Call the function. Build and so what does it take? It takes the data and n. So model equals build n-gram. Given sorry, so we'll use the train data. It will take a bit of time, and let's see. Okay, so let's check the perplexity when n equals 4. So it's 4, so that's really low. Let's see when n equals 3, 11. Say when n equals 2. Okay, so it's clear that when we increase the size of the n-gram, the perplexity gets lower, which is good. But this is for the training data. Let's see for the validation data. Okay, let's see when n equals 3, it's 36. When n equals 4, it's 44. But and yeah, so this is good. Okay, now we need to get a probability distribution. So we need to, given a model, given a context, we need to find the words and their respective probabilities given this context. So suppose I have my data is like this, this is a cat, this is a dog, this is a tree. So this is my data, and I already have the model. I need this function to return a dictionary that maps the word given the context, and the map gives the probability of the word given its context. So in this, if this is my data, so I need this function to return the probability of given this context. So context is going to be this is a, and the output of this function should be cat, the probability is 0.33, dog, the probability will be equal 0.33, and tree, the probability is going to be 0.33. And if we have another, this is a cat, then in this case cat will be 0.5 and dog will be 0.25 and tree will be 0.25 as well. Okay, so using our model, we just need to return all the possible words that will come after this context and their probabilities, because we are going to use this information in order to generate text. Okay, so how am I going to do that? So first, so what will come into your mind is we can just use return model of context, right? Because we already built that in our context. However, this context may not appear in our n-gram model. So what we can do is we do another recursion just like what we did before. So if context in model, return the model of the context. However, if it doesn't appear, else return get proper distribution of the model, but this time we'll take the context, we'll do the smaller gram context. Okay, it's the same, it's just like what we did here. but we are not going to multiply with 0.4 because we are not interested in the actual number of the probability. We need to find all the words, all the possible words and their probabilities. And if the larger gram is not in our context, we will use the smaller gram, and we'll do it recursively because if the let's suppose it's n equals to 5, and if the given my word now, the past 4 words do not appear in my dictionary, I will check the last 3 words, and if they do not appear in my dictionary, I will check the past 2 words, and so on, okay, until I find the smaller n-gram that will satisfy my needs, okay? So okay, so let's move to our final function. Okay, it's the function that we are which is going to generate a sentence. Okay, so now given a now because using this function, given any context, we will have a number of words and their probabilities. We can sample from them in order to generate. So as an example, suppose we start with this, and based on the probabilities of all the words that we have, let's say if this has a probability of 0.9, that have a probability of 0.001, this cat has a probability of 0.009, and now suppose we're starting with this, the most probable word that which we are going to use is, so we're going to use is, for example. We will pick a word randomly, but is, because it has the largest probability, we're going to use it here. And now given this is, we will have the probability distribution of the next words could be, let's suppose I will have a probability of 0.8, and we'll have a probability, let's say, of 0.2, and this time we're going to sample one of them, and so on and forth. So we will build our sentence, we'll generate a word, and then our word will be our next context, and so on. So in this case here, we'll start the sentence with a start token, and then using the probability distribution that we're going to build here, given a context, we will get a word. Okay, we'll get a set of words, we're going to use one of them based on their probabilities, and using this function we can generate words. So how we're going to do that? So we have 2 stopping criteria. First, if the final token is not the end token, so this end token will have a large probability to appear after a dot. So if we are building a sentence and then we by chance we got into a dot or a period, then the next token will very likely to be the end token. And there's also a condition, because we don't want our sentences to be very long. We'll stop it if it doesn't stop, if the end token doesn't appear, and the length of the sentence will be 100. So first of all, we'll get the probability, the probability equals get prob of model, and then tuple of sentence. Okay, and now given this probability, we can use the nice function from NumPy. So it's called NumPy np.random.choice. So given a list, okay, and given the probability of each element in the set, is going to return a number of elements. So as an example, suppose I have a list like this, A, B, C, and their probabilities are 0.1, 0.6, and 0.3. So if I say mp.random.choice, this is my x, and this is p, okay? And if I choose one, if I write one here, if I call this function, it's going to return me one element that is sampled randomly from this list according to this probability. So if I run it like 100 times, B will appear 60% of them, A will appear approximately 10% of them, and C will appear 30% of the times. Okay, so this is the mp.random.choice. So what am I going to do here is I'm going to get a word. So the word is going to be mp.random.choice of list of proba.keys. Okay, so I will use the keys of the keys of my probabilities. So because this is a dictionary that maps words to probabilities, so I will use the keys. These are my words. How many parentheses I have? Yeah, I think that's right. And I will sample one word, and then the probabilities are going to be the values of this dictionary. Okay, so B is going to be list of proba.values. Okay, now when I sample this word, I'm going to append it to my sentence. So I'll go sentence dot append W of 0, because W is an element in a dictionary, so it's a word and its probability. I'm not interested in the probability, I'm more interested in the word, so I'm going to append it in my sentence. So the next time my sentence here will going to be larger, and I will pass it to my get probability distribution. I will get another word, I will get the probability distribution here, and then I will sample another word from this list, okay, using the probabilities. I will append it, and so on and so forth, until I sample the end token, or my length of sentence will be 100, and then I'll stop. Okay, let's see. Okay, so this is the first sentence that's generated. So a population policy should be to train the mind. Okay, so it's not a very good one. Let's try again. Don't mess me around. Makes sense. I am helping you. It's a perfectly good sentence. So this is how we can use the Ngram models to generate sentences. You can play with it a little and see what sentences you will get. Okay, I am a cook. The changes were not made. So these are, they make sense. I mean, syntactically they are right, but some of them will be completely nonsensical. I mean, the syntax will be good, but the semantics will be a little bit tricky. But because in the end, the Ngram models doesn't capture very long dependencies, so they can capture a very small, let's say, dependency between the words. So the generated text will be good in syntax, but will be bad in semantics. Okay.